Displacement model. Displacement model. Because in all these elements, once we treat only at the nodes, at the ends. In first order basic element, only in case of line element, only two nodes will be there, and at two nodes only we have to select the variable. The variable, we call it as the degrees of freedom, usually the linear displacement or angular displacement. So in bar type of problem, bars, analysis of bars or spring elements, so there will be only axial deformation, no other type. Even if it is inclined also, it will be axial only. No question of any other displacement. It will be along the axis only in the case of bars. In the case of bar elements, the displacement is only along the axis of the element. No other way. Even if the element is inclined, there is no component, resolution of the component involved. It is only one direction, that is along the axis, that is along the local axis. The force or displacement in case of bar problems or spring type of problem, it will be only axial. When you come for truss, though it is one-dimensional, similar to bar, it is also subject to only axial force, but load may be at the joint in different direction, in any direction. It cannot be along the axis. In any direction at the ends, load or displacement, it can occur in any direction, but only linear dimension, no angular displacement. In case of the because each joint is thin joint, only angular type of displacement, only linear type of displacement. So that linear type of displacement, in case of plane trusses, it can resolve along our two fundamental global directions, x and y, that is two components we get displacement. In case of any node of a truss, clear the unknown displacement and the model equation we have to write. In case of space truss, it is also one-dimensional, but whatever the displacement of force, it will have components in three directions, x, y, z. In plane trusses, it is only two. In case of space truss, it will be in three directions. Of course, space analysis is not there, only plane truss analysis is there in your syllabus, only 2 degrees of freedom. That is called degrees of freedom. General displacement at each node will be only 1 in case of bar problem, only 2 in case of per node. I am talking about per node 2 unknown displacement models. In case of space truss, 3. In case of beam, at each node, again beam can be modeled using a line element. So at each node you have 2 types of displacement because beams we assume it to be axially rigid, and only 2 displacements because beam is a planar structure. In plane structure only 3 possible displacements at each node. Out of 3, the horizontal is not there. The left with is only vertical and rotation. Only 2 degrees of freedom per node in case of beam problems. All are one-dimensional. In case of rigid plane frame problem, you have 3 degrees of freedom. Horizontal, vertical, as well as it can happen in any direction, but you can, for analysis purpose, we are resolving that only along 3 basic global directions. So yes, in B it is only 2 rigid plane frame, 3, 2 translations and 1 rotation. In space frames, it will be 6, 3 translations and 3 rotations. So those are the classifications you have. You have analysis of planar structures only, so only beams, rigid plane frame, plane trusses. So at each node, how many displacements, that also I have told you. In case of bar problems, it will be only 1. In case of truss element, you have 2 per node. That is 2 translations. that is like this. In case of bar, whether it is global or horizontal inclined, it is only axial. So only this. This is bar. In case of truss, in plane truss, in case of plane truss element, so in the local coordinate, you have only one. This is u dash, this is uj dash, u I dash, I j. Two nodes here, I, j. Only one node, displacement. Here it is local coordinate, it is only one with subscript I have given. In global, you have two displacements. U, V, Uj, Vj, Ui, like that. That means at each node you have two displacement. In global coordinates I am talking about. In local coordinates it is only one. In global it is two. Here, whether it is local or global, it is only one. That's the difference between bar and truss. 1 degree of freedom per node, 2 degree of freedom per node. In case of beam, again, beam, it may be straight or it may be inclined also. Beams may be inclined. It need not be straight, it may be inclined also. So even if it is inclined, then in case of beams, we have only 2 degrees of freedom. So here we take rotation anti-clockwise as positive finite element approach. That's the only change. So other one, translation in global direction, left to right positive, bottom to top positive. That's the positive direction only I am showing the displacement. Here you have only 2 displacement, one translation, rotation. Axial is not there. Here also inclined beam, axial is not there, only shear, even if the beam is inclined. Okay. But if you come for global, only component of this will be there, vertical component. So in the global direction for beams, you have 3, but in local, we are interested in the internal forces developed only in local coordinates that you have seen in classical approach. Final results will be only with respect to local coordinate. Even if it is inclined, you have in local coordinate only 2 degrees of freedom, not 3. But in global direction, it can have 3, because component of this horizontal, vertical and rotation. 3 will be there. That's the difference between beam and rigid plane frame. Right? So this is in case of beams, inclined beam and of course usual horizontal beam. Normally beams we define as the one wherein it is along a line or members. Right? Even it may be inclined, but again we take only 2 degrees of freedom per node. Whereas in case of rigid plane frame member, you have all the 3 like that. At any node, you have maximum 3 degrees of freedom. That's why syllabus clearly says maximum 3 degrees of freedom. Even if it is bar type, only 1, truss 2, beam 2, rigid plane frame, it is 3 degrees of freedom per node, 3 displacements. And we have to select the model, which having understood the type of degrees of freedom. I'm not talking about kinematic indeterminacy. Kinematic indeterminacy is referred to the unknown displacement to be determined during analysis. That is, the restraints will be removed because each joint in a structure, it need not be free. It will be having restraints, especially at the boundary. So you have to remove all those restraints from the general degrees of freedom. That removed portion, after removing whatever left out, that we call the kinematic indeterminacy. But degrees of freedom is general total displacements which are possible in the structure, irrespective of restraints. Afterwards, you will impose the boundary conditions, right? First, by formulating the equation, you don't impose any boundary condition. You will assume each ends to be free. It has to follow rigid body motion. That I will set out the criteria. Each body has to undergo, capable of undergoing rigid body motion mode. That means it has to bodily move. There should not be any contraction or elongation within the body. Body, whatever left hand moves, same amount right hand also should move. Like that. It is a rigid body motion. Body, there won't be any contraction or elongation resulted. That is the primary criteria to be satisfied while choosing the displacement model, rigid body motion, constant state of strain, continuous state of, that I will tell immediately in this. No. So now I am talking about degrees of freedom for 9 element nodes. Like that, your other 2 dimension also, depending upon plane stress, plane strain problem, or axial symmetric problem, or usual 3D problems, you have degrees of freedom. For that degrees of freedom, which are possible movements, either translated type or angular type, you have to choose a suitable model. That is the main thing which is there in second step. The unknown, how to model that unknown. Usually unknown will be displacement. In other problems, fluid flow problems, it will be fluid velocity. Velocity will be the problem. Like that, in your heat transfer problem, heat mass transfer problem, heat will be the flowing thing, variable. Like that, variable will change. Field variable depending upon the type of problem. Right? So, depending upon that, now you have to choose the displacement model. So, the displacement model. So, the displacement model. Displacement model. Usually the displacement at any point within the element, at any point within the element is chosen in the form of a polynomial equation with some parameters. With some coefficients, parameters, which we have to determine, right? Parameters satisfying the following conditions. That conditions, we call it as convergence criterion for the displacement model. So it is called convergence criterion. But in the previous class, I told the final, this is basically approximate method of analysis. Finally, the result has to converge to the exact value. So to achieve that particular thing, certain conditions to be satisfied. That is why it is called as convergence criterion. So as to arrive at the exact solution, that is, solution is your displacement itself, which is unknown. That displacement, whatever you are determining after choosing this model, that displacement should be exact, or more or less with little variance from the exact results, with permissible variance with the exact results. So to have that particular solution within the limits, we have to satisfy certain criterions laid down by choosing the displacement model itself. That is called convergence criterion. So the convergence criterion are, the first criterion is that displacement model or equation which you choose, it should be continuous and complete. So that's the first criterion, the displacement function or model chosen should be continuous and complete. At all points in the element. Within the element, at all the points. So it should be continuous. Continuous means it should follow that chain reaction. That displacement should move without any obstruction or without any break. Without displacement becoming zero. It should not become zero all of a sudden at some points. It should be continuous throughout, except maybe at the boundaries. Except at the boundaries, at all other points, it should be continuous. At all the points, the elements will be continuous and this displacement also continuous. Rigid body I told. That's why there should not be any change, relaxation or contraction. Bodily it has to move. So due to the forces. That is why it should be continuous. I hope I made with you what is this continuous understand by you. So that can be achieved by choosing a continuous polynomial equation. X, some constant c1 plus c2x, c3x squared, c4x cubed, c5x4 like that. Continuous polynomial of nth order. If you choose, then it will be continuous. That's the very first condition which we have to choose for a displacement. Then second condition is the displacement function chosen. The displacement function or model or parameter. A displacement function should follow rigid body motion. Right. So in the element should be capable of undergoing rigid body motion. Bodily it has to move. It should not undergo any change in the displacement or distortion. Body should not undergo any distortion. That's what I meant. The moment distortion occurs, there will be change in the. There should not be any distortion. There should not be any change in the body. It should be rigid. It should be rigid body motion. It should happen within the body due to the motions. So that is your second condition. So this is achieved. This is achieved through a polynomial equation with constant term. With a constant term. The polynomial should have a constant term with it, not variable term or constant term. Or one, first we choose a constant term. To see that at all other points x is equal to 0, especially at the boundaries, we should not become 0 at all. That should not be any discontinuity, should be continuous. By choosing a constant term in the polynomial, we can achieve this condition. The third condition is the displacement function. Displacement function should represent a state of constant strength. Constant strength. It's a very important aspect. It should satisfy the state of constant strain at all the points. The displacement model, whatever you choose, or equation, whatever you choose, should be able to represent a state of constant strain. That means constant state of strain is after all derivative, change in the displacement. So that is maybe first derivative, slope, second derivative, curvature, like that. That for derivatives should be there, should be present. It should not become 0. That's called constant state of strain. Even the strain, if it is there, then it should be a state of constant strain. It should not become totally 0. So that is why you should have a lower order term in your polynomial, x or y. In the planar structure, the variable will be x or y. If you differentiate with respect to x or y, it should not become 0. First derivative. That's the first change in the displacement. If at all it has to happen. Because after all strain is delta u by delta x. Or delta u by delta x square. That's curvature. That strain should exist, it should not become 0. Right? Is it clear now? Convergence criterion, it is very, very important. So, this particular condition is achieved by having lower order terms in the polynomial. Choosing lower order terms in polynomial satisfy these conditions. That is state of constant strain state. It is achieved by having lower order term. Constant term you should have first to start with. It is a must. Lower order term is a must to achieve this state of constant strain. And continuity is a must. Complete means, I will explain in the fourth condition, the continuity condition. That is fourth condition is the displacement function chosen. The displacement function chosen should not have any preferred direction, should not have any preferred direction. So you should have a constant orientation. You should not be disturbed as such from one to another position. So that is that. So this particular condition, we call it as the geometric isotropy. Geometric isotropy. That is, geometric isotropy has to be satisfied. Geometric isotropy, it has to be satisfied. So usually this is achieved by what is known as a Pascal triangle. So this is usually by using the term and choosing the other terms. One term you should have choose a constant. You should choose lower order term. other terms, whatever you are choosing, other higher order terms in the polynomial, you can choose in such a way that the geometric isotropy is satisfied. You should not have any preferred direction. You should be perfectly symmetric about a line, about an axis of symmetry. So that is, the geometric isotropy has to be satisfied. That is, this Pascal triangle should be satisfied. So the terms should be like that. The Pascal triangle will give, you have to choose the terms of the polynomial like that. Constant term, one, you have to choose alpha 1 or one figure. Next, if it is a two-dimensional body, I will take a two because these are all planar structures. They should lie in one plane. So plane means you should have two directions, x, y, minimum. So there may be one variable x or another variable lower order term. If it is along x, you take, if the structure lies along x direction, you take x as a variable. 1, x squared, x cubed, x4, like that. If it is in the y direction, because in the plane only we are talking about, it has to be 1, y squared, y cubed, along that line, if it is one dimension. If it is two dimensional, it should be symmetric about this line. It should not have any preferred direction. That is what it means. This is axis of symmetry. So the other higher order term, say x squared, second term is 1, then x squared, then xy, y squared. You have to choose x squared term, y squared term, xy term also. Then only it will be complete, continuous. You should not choose only x squared, or you should not choose only y squared. Or you should not choose, you can choose xy. Not x squared, y squared, you can choose xy. If your polynomial equation will consist of only 4 constants, say, then 1 x, y, xy you can choose. If it is 5, then 1 x, y, x squared, y squared. You can choose together, but not one term. This is a must to satisfy the other two criteria. Constant is a must, lower order term. Higher one, you should satisfy continuity, you should not have any preferred direction. Suppose if it has to be a cubic polynomial, so this is linear polynomial, this is this is linear polynomial, this is constant polynomial, linear polynomial, this is quadratic polynomial, quadratic polynomial equation, or it may be cubic polynomial, x cubed, then xy squared, x squared y, then y cubed. It has to be like that. See, it is perfectly symmetric. The terms has to be like that. That is this geometric isotropy, or it is Pascal triangle. Right? For three-dimensional thing, it has to be Pascal. Again, Pascal triangle with 3D, x, y, z. All these three things will select. So for other here order, say x4, it has to be here x cubed y, then x squared y squared, then x y cubed, then y4. Like that. This is called Pascal triangle. You can choose your polynomial equation. Say u is equal to alpha 1, or u is equal to alpha 1 plus alpha 2x plus alpha 3y, or alpha 1 x, alpha 2 alpha 1, alpha 2 x, alpha 3y, alpha 4 x squared, alpha 5, so like that. If it is cubic polynomial like that. So this is how you have to select a displacement model. These are called convergence criteria. First condition is should be continuous, complete. Complete means this is what I told. All the terms, coefficients must be present in the polynomial. You should follow rigid body motion, constant. You should follow constant state of strength. You should not have any preferred direction. So these are the conditions should be followed, and they are called convergence criteria for the displacement model. That is the second step. You have to choose a suitable model or equation for representing the unknown field variable at each node. Depending upon number of displacement, you have to choose the model. Then you have to substitute those, choose the model, substitute the unknown displacements at x is equal to 0 or 1 point, another point. So you represent an equation of the form moving displacement at any point as some function into the nodal displacements in terms of nodal displacement. And this function, we call it as the shape function. Shape function definition is, it is that function, that parameter, which when multiplied by nodal displacement, nodes you have already defined, 2 nodes, 3 nodes, whatever it is per element, and you know the displacement, degrees of freedom I have told, in terms of the degrees of freedom at each node, you can represent through a function the displacement at any point. That is called the final displacement model. Right? Then we have to find third step. Go to the third step. Right? Both first step discretization, second step displacement model, it is very important. Then third, fourth element property, strain, stress, you have from theory of elasticity, you have ready-made equation for strain, stress, strain energy, and energy potential. You can find the element property K. That's all. That's the main subject of this finite element analysis. For all the family of finite elements, we have to get this. That's all the subject matter. Nothing other than that. Right? Next, we will go for the model, displacement model actually. I have already defined now the term called shape function. Shape function. That is, displace the shape. How it will be, that shape, how that displace is. What are the value of displacements at various points? We have to arrive at a suitable equation. So, first I will define what is a shape function. So, the shape function is defined as the one which when multiplied by nodal displacement vector, maybe nodal displacement vector in global coordinate, or it may be natural coordinate, one more coordinate I will explain now, natural coordinate or Cartesian coordinate. Maybe global coordinate or in Cartesian, in local coordinate, or it is natural coordinate system. there are three coordinate systems now. Earlier, in classical method, I have explained what is global coordinate system, local coordinate system. Now also I told, at each node, you can add displacement variable either along local axis. There one of the axes is along, one of the axis, coordinate axis will be along the axis of the member itself. In global, it is horizontal, vertical. Other one will be normal. There, in local, along the axis 1, other 2 orthogonal are the coordinates. We have another coordinate system, natural, which I am going to define now. So you can define this displacement either in global coordinate system or local coordinate system or natural coordinate system. Either one you can define by coordinate systems. The element, whatever I told, 9 element, you can define with respect to any one of these type of coordinate system. So with respect, after defining this, you have to show the component of this displacement. Right? Along these components of the displacement, along this direction, because displacement is a vector quantity, so you should have direction. You are choosing the direction in any one of these ways. So out of this, you have to choose the nodal displacement. In that nodal displacement, that is what we have to determine during analysis, find it. So that displacement, if you have to express it in terms of a function, and that will give you the displacement at any point. So the shape function is defined as the one which when multiplied by nodal displacement vector, which is represented in any one of these coordinate system, will give the displacement at any point within the element, that is the definition. Suppose if you take a line element having 2 nodes, end nodes I know. So I will take a bar element it is. So it will have one displacement, another displacement. So this is node I, node J of the bar element. So this is the nodal displacement Ui or Qi, either Q dash I or Qi. Qi is this global coordinate system along global direction. It is same in case of bar element I told. In case of trace element, global displacement will be horizontal, Qi. This is Q2 vertical. Like that, different thing, two things. That you have to mark it. Suppose here it is Qi, this is Qj, then at any point the displacement Q is equal to say N1 Qi plus N2 Qj. Some function into nodal displacement I, some other function into nodal displacement J will give you displacement at any point. So all in matrix form, I can write this as Q is equal to N1, N2, N2, Qi, Qj. This is called Q is equal to N into some D, nodal displacement vector, D, Q, whatever it is. At any point, or this I will call U, then U, this you can call it as Q. Displacement at any point. U or Q. In terms of nodal displacement vector, Q is the nodal displacement vector, Q is Qi, Qj, or Q1, Q2, Q3, Q4, like that, whatever it is. nodal displacements. This is displacement at any point. So this nodal displacement at any point multiplied by a factor called shape function. So this we have to determine. This you can determine the moment you choose a displacement model. For that, so u is equal to, in the form of polynomial, you can choose it. Right? Or you can use what is known as Lagrangian formula. You can choose the shape function. Straight away. Lagrangian formula is easier for along a line to choose the shape function. Along either x-axis or y, or both x-y, if it is a plane figure. Both you can choose it. So that's about shape function and displacement model, various aspects of displacement. Displacement at any point and displacement at the major nodal points which we have to determine. All these points. Next, I will explain what is this natural coordinate system. That's one thing which is remaining. If I explain this natural coordinate system, then all our unit 4, up to unit 4, the theory aspects is covered. Then only the element property I have to tell how to arrive at that stiffness matrix by potential energy. So that completes all your theory portion. Then straight away we can work problems based on this theory in one. Nothing else than that. All the 5 units will be covered there. So next we will take up what is known as natural coordinates, which is a very, very important aspect.